All right, so real quick, we're going to go over impulse momentum. This is the last new section of material before your final. So after impulse momentum one, you guys should have all of the knowledge you need to start studying for the final. So really quickly, what we've gone over so far. Sorry, this is such like an ugly, like half blank slide, but I kind of put all the notes in this picture already, so I didn't want to waste too much time retyping it. Um, Essentially, the three parts of kinetics that we've gone over so far are force acceleration, which is basically straight up Newton's second law. So it's just force is mass times acceleration. So basically, what you do is you sum up all of the forces in the system and you set it equal to the sum of all possible movements or accelerations caused by that series of forces. And basically, you evaluate it in all three directions. So you evaluate it in the x direction, the y direction, and then in the rotational direction. So you have three equations because you're evaluating three dimensions, so three unknowns. Your work energy equation is kind of like a derivative of, or well, not, I don't want to say derivative, but um, stems from the Newton's second law equation. So if you integrate the forces, you get work. And if you integrate mass times acceleration, you get a change in potential or kinetic energy. So change in anything is always final minus initial. So if you do final minus initial, move initial over here, you get your work energy equation, right? So you have the initial kinetic energy, which is usually what's given in the problem, and then it's some work done on that body, and then you have to find what that does to the final kinetic energy, or what that means for the final kinetic energy. But all of this is done in one equation, right? So it's the initial kinetic energy of the system, the sum of the total work done on the system by all of the forces, again, summed up. And then that is the final kinetic energy of the system. So because you have this one equation, you can only solve for one unknown. So you can either solve for the final kinetic energy or one of the velocities or something like that. So you can only have one unknown in this situation. And that basically um, is the core part of work energy. Now, work energy has all these really ugly equations that comes with it, but you're given most of it on your equation sheet. So for weight, you're given that the work done by weight is plus or minus the magnitude of the weight times delta y. You're given that the friction is the negative friction force times the distance that it's traveled, and that you're given that the work done by a spring is 1/2 of the spring constant times the difference of the squared displacements, right? So you're given essentially these three here. You're going to have to know or be comfortable using these three, or you're going to have to know how to get from these three to probably the easier version of them, right? But all of those are definitions, right? So weight obviously stays the same because you can't really do much to that. But delta y is the difference between height 2 minus height 1. The friction force can be rewritten as mu sub k times n, and the difference in the distance is just d2 minus d1. The spring constant is still negative 1/2 k, but these displacements here are the final length minus the initial length squared. So it's just defining displacement, right? It's the change in length. And then the work done by force and a couple moment are not defined because that's the definition of work, right? So the definition of work is the integral of force over a certain distance, or the integral of a couple over a certain angle, right? So that's not given because that's the definition of work. But other than that, this is essentially just the integral of this with respect to position, right? Well, impulse momentum is the integration of F equals ma with respect to time now. So instead of ds, it's dt. So again, if you integrate force over a certain time period, you're going to get an impulse, right? And if you integrate mass times acceleration over a certain period of time, you're going to get momentum, right? So again, mass times acceleration integrated gets mass times velocity over a certain time. So basically you can write it as mass times the velocity at a certain final point minus mass times the velocity at a certain initial point, moving this term over here, you get whatever the initial linear momentum is, which is directly related to the linear momentum or the linear velocity of the body, right? Plus the integral of the forces acting on the body from the given time frame, right? And then that's going to equal your final linear momentum, right? So essentially you have a very, very similar relationship, a very similar process to get to the equations, and really a very similar way of solving it. And like work energy has the linear and the angular, you have that here. So basically you're going to look at forces and mass times velocity, or you're going to look at moments or couples and IG omega, right? So basically the only other different thing about this problem, or this type of problem, I should say, is that you have to draw diagrams again, right? So in your initial steps, right, you should classify motion, obviously, you should write your properties, and then after you write your properties, you write essentially this equation, right? So you draw whatever shape you're looking at, and then you look at all of the ways that that shape can move. So is it moving vertically? Is it moving horizontally? Not how it can move, how it is moving in the problem. Or is it rotating, right? So you draw whatever it's actually doing. And then you draw it again, added with the integral around it with respect to time. This part's important. Don't forget that part. You draw it with respect to time, with all of the forces acting on that. So that might be a weight, that might be a couple moment, that might be an applied force, might be multiple applied forces. Just draw everything acting on your body. And then set that equal to however that body is going to move because of it. So I know one of the worksheets was a rocket with thrusters on it. And obviously, because it was an applied couple, it's only going to cause a change in rotation. But if it's a force applied at an angle with a couple, basically you're going to have, so basically three forces now. So the couple, so two forces that form a couple plus that third force at an angle, you're going to have all three of these unknowns. And then for whatever unknowns you have here, you're going to look at what you have here and what you have here. So you're going to have one equation for essentially each of the unknowns you have here in this final piece. So then you just solve like normal. So you look at, if it's the rotation, you take the initial rotation plus the moment about this center point with respect to time, the integral of all of the forces causing a moment with respect to time. The important thing to remember is that a moment is a force times a distance. So if it's a curved arrow like this, or if it's an applied moment like in this problem here, you don't have to multiply it by a distance because it's already a moment. But if there was a vertical force here on this edge, you have to multiply it by the distance between that edge and that center point, right? And then you set it equal to the final IG omega. Other than that, this is pretty straightforward. Oh, one thing I also wanted to cover in this video is how to decide which one to use, right? So forced acceleration is if you're given anything about acceleration, right? Because you're not really using acceleration anywhere else. Work energy and impulse momentum both use velocities, right? Because this is 1/2 mv squared, this is mass times velocity. But work energy, you have to know some kind of change in position, right? Because you're integrating with respect to s, or with respect to position. With impulse momentum, if you're given a time frame, that's when you're going to use impulse momentum because you're integrating with respect to time now. So this entire equation is based on time. So other than that, that's all I really have. Friendly reminder to go to office hours. Your final is coming up pretty soon. I believe the final's on the 9th at 8:15 at night in Seidler Hall 114, I believe it is. And the other thing I wanted to announce is that my review session for the final is going to be on December 5th, whatever that Saturday is. I think it's the 5th, from noon to 2. So be there, be square. And that's all I really had for today.